Hi there. Chapter 14.8 today. This is actually the last chapter and the last lesson for the pure Year 12 book. So we've come to the end of not only the chapter but the entire book today as we wrap up exponentials and logs. So in this lesson I'm going to have a look at how some graphs don't fit to straight lines, nor do they fit to, for example, a quadratic, cubic or quartic graph. Sometimes we have exponential graphs which need to be modelled with exponential equations. So we're going to show you how to graph those and solve questions based on graphing in contexts. So first of all, before anything else, as ever, here's 4 warm-up questions for you to try. 1, 2, 3 and 4. So press pause on the video now, copy them down, have a go. When you're ready for the answers, press play and I'll talk you through them. So let's start with question 1. So we have an exponential curve C1 defined as y equals ab to the power x. A and b are positive constants. So it tells us here they're positive. Very good. So C1 passes through points 1, 0.6 and also 3, 5.4 for the values of a and b. Here what we have in essence is some simultaneous equations we can set up ready to go. So we know one point is when x is 1, y is 0.6. So we can substitute in this one here straight away. And so when y is 0.6, 0.6 is going to equal a multiplied by b to the power 1, because x is 1. But b to the power 1 will just be b. In the same way, we also know that when x is 3, y is 5.4. So we can use this and input these two variables x and y into an equation to give us some more information. So when y is 5.4, that's going to be the same as a multiplied by b to the power x. So when x is 3, that's going to be b cubed. So from these two now, what we can do, we can eliminate a, we can do the bottom equation divided by the top. So if we just do the bottom divided by the top, what we get there is 0.6 divided into 5.4, that gives us 9. The a's cancel. B cubed divided by 3, sorry, b cubed divided by b gives us b squared. Therefore, b must be 3. If you're thinking, well, can't it be minus 3? Isn't b plus or minus 3? Remember how a and b were set up as positive constants. So now we know that b is 3, we can now sub this back in to the blue equation, or even the green. So substitute this into the blue equation. What we get now is 0.6 equals whatever a is, multiplied by b. We've worked out that b is 3. So therefore, divide through both sides by 3, we get that a must be 0.2. Hence we've cracked question 1. Question 2, very much the same idea really. Here it's a slightly different exponential, but we can use the same process. So we've got that this curve passes through 1 and 0.5. So when x is 1, y is 0.5. So 0.5 equals whatever c is, multiplied by whatever x is, in this case 1, to the power d. So 1 to the power anything is just going to be 1. So therefore we can just simplify this and just say that c must be 0.5. Okay, we also know here that the point 4,8 is on this curve. And so if we just substitute these values in to the equation, now we know that c is 0.5, we get that 8, which is y, equals c, which is 0.5, multiplied by x to the power d. We know that x is 4, so that's 4 to the power d. We can now divide through by 0.5, which is the same as doubling, so we get 16 equals 4 to the power d, and therefore, what power of 4 gives 16? It's obviously 2, so d must be equal to 2. Question 3 next. I've got this straight line graph, I throw back to GCSE days. First of all, we need to draw a line of best fit for the data set plotted in figure 1, where figure 1 is the graph. So I'm not going to muck about. Here's a line of best fit I drew earlier. Here we go. There it is in red. And now, using whatever line you've drawn, we need to estimate the equation of this line of best fit. So for me, we need to remember where it crosses the y-axis. That's the value of a constant. So for mine, I'm getting here that the intercept is 3.2. Okay, so I can just write that down. So the intercept, I'll say the y-intercept, that equals 3.2. And to find the gradient, I just need to take 2 points on the graph. So if I take, well, I don't know, that point there, that looks fine to me. And also I can take the point at 8, and that looks to me to be 11.6. So now we need to estimate the gradient based on these points. So I'll take this line here and use this to map out the gradient. So let's have a look. So the gradient is obviously the change in y divided by the change in x between any two given points. So what I need to do is to calculate it for these 2 points here. So if I just pick here these 2 points, which I've highlighted in blue, the gradient is going to be the change in y over the change in x. So let's calculate this between these 2 points. You could have picked different points, obviously, if you wanted to, whichever points look fairly obvious to you. So between here and here, that's 11.6, and down here, where it crossed the y-axis, that's 3.2. So the change in y is 11.6 minus 3.2, and the change in x is from 8 down to 0, which is obviously just 8. And so if I just input this now into the calculator, so we have 11.6 minus 3.2, all of which we divide by 8, and I get 21 over 20, which is the same as 1.05. So now we know the y-intercept and the gradient, we can apply the idea of y equals mx plus c to this, and we can work out that the line of best fit is going to be y equals the gradient, which we've calculated an estimate for here, 1.05, x plus the intercept, which we worked out as 3.2. Finally now for the warm-up, question 4, Calculus Corner. We're given the gradient of a curve, we're given the gradient function here, dy by dx, and we're also told here that the point 1,4 lies on the curve. We need to now find an equation for the curve C in the form y equals fx. So what I'm going to suggest we do first of all is expand this out. We get dy by dx, expand out 3x squared, we get 9x squared. We must double the product, so 3x times minus 1, then double it, it gives us minus 6x. Square the last term, square of minus 1 is positive 1, and that's the gradient function expanded out. Now we need to remember that when we go from dy by dx to y, we need to integrate. So we're going to integrate this expression here with respect to x. So we're going to integrate 9x squared minus 6x plus 1 with respect to x. So first of all, we look at this x, we do it piece by piece, so we do the first term first. We take the power of x squared, we increase it by 1, then divide through by the new power. So the new power will be 3, so it's going to be 9x cubed divided by 3, which will give us 3x cubed. Over here, x to the power 1 becomes x squared, and then we divide all of this through by 2. So minus 6 is going to become minus 6 over 2, which is minus 3. We get the x squared. The constant term 1, we increase the power of x from a 0 to a 1. So the 1 just becomes 1x. And really important, we need to remember the constant of integration, c. Now we need to work out what this constant of integration is using this information here, that the point 1, 4 lies on the curve. So now what we need to do is sub in the value x equals 1 and y equals 4. So when y is 4, y equals this expression here. So 3 times 1 cubed is 3, minus 3x squared. So minus 3 times 1 squared, that's minus 3. And plus x, so plus 1. And plus c. Therefore, 3 minus 3 plus 1 just gives us 1. 1 plus 3 gives us 4, so c must be equal to 3. So therefore, y, which we're told is f of x, is 3x cubed minus 3x squared plus x, and plus the constant of integration, which we've worked out, is 3. And that's all of the warm-up questions completed. Now the main part of the lesson. Logarithms and non-linear data. So first of all, let's consider an exponential function, f of x equals 0.2 multiplied by 3 to the power x, where x is any real number. So if we were to imagine this here, we could actually sketch this out on a graph. So label any points of intersection of the coordinate axes and also any asymptotes. So what we need to remember here is we can work out the sketch by inputting certain values. So for example, when x is equal to 0, y is going to be 0.2 multiplied by 3 to the 0. Anything to the power 0 is 1, so y is going to be 0.2. So it's going to cross the y-axis at 0.2. In fact, to help the sketch, I'm going to label that in after, but it's going to cross the y-axis at 0.2. Think about what happens as x gets bigger. So as x goes towards the direction of infinity, y is also going to go towards infinity. For example, 0.2 times 3 to the million. 3 to the million is pretty damn big, so even when you times it by 0.2, it's still going to be pretty huge. Going the other way around, as x goes smaller and smaller in the direction of negative infinity, y is going to go down towards 0 because 3 to the negative x is the same as 1 over 3 to the power x. So as x gets bigger and bigger, 3 to the power minus x gets smaller and smaller until it gets closer and closer to 0. So y is going to go towards 0.2 multiplied by 0, which is 0. Therefore, there's going to be an asymptote here along the x-axis. So that tells us there's going to be an asymptote at y equals 0, which is the x-axis. So now it comes to sketching it, which I absolutely hate doing because I'm terrible. So it's going to start here, go up and up and up, hugely. I'll get rid of that little tail at the end, I didn't want that. There we go. So it's going to cross at 0.2. Oops, not intended. Pardon me. So that's going to be 0.2. And that's going to go closer and closer to y equals 0 without actually quite technically ever touching it. So as you can see, long story cut short, that is not a straight line, that is an exponential curve going whoosh really high as x goes bigger. However, think of this. Imagine now we took f of x here and then took the log of f of x. So let's just try and fill in this table. So when x is minus 1, y, which is f of x, is going to be 0.2 multiplied by 3 to the minus 1. So let's just see what that gives us. So 0.2 multiplied by 3 to the power of minus 1. That gives us 1 over 15, which is to one decimal place 0.07. Whoops. Oh, we're going to write each log to one decimal place, that's fine. So this one here is 0.0667. I'll give that to 3 sig figs. So 0.0667. When x is 0, that's going to be 0.2. Again, you can try with a calculator. When x is 1, 0.2 times 3 to the 1, 0.2 multiplied by 3 is 0.6. When x is 2, 0.2 times 3 squared, 0.2 times 9, that's going to be 1.8. As you can see, these figures are increasing by a multiple of 3 each time. So this one, 1.8 times 3, that's going to give us 5.4. Now if we take the log of these values here, let's see what happens. So this one is for x equals minus 1. So if it just says log, by the way, like I've put here, log refers to log base 10, which is the common logarithm. Just as you have ln, which means log natural, for natural log, that's base e, you don't need to put ln subscript e. It's just assumed that people know that that's base e. In the same way, if you write log with no base, it can safely be assumed that the base will always be 10, unless otherwise stated. So here, let's take the log of each one of these. So the first one, log base 10, the answer I stored in the calculator, that was minus 1.17. So to one decimal place, that's minus 1.2. Then log of 0.2, that's what that gives us here. Log of 0.2, I get to one decimal place minus 0.7. Log of 0.6, it gives me minus 0.2. Log of 1.8, oops, 1.8, that's going to give me 0.25, which to one decimal place is 0.3. And then finally log of 5.4, if we work this one out here, we get 0.7 to one decimal place at least. So now we've got this data here. We can plot a graph of not x against y, but we can plot a graph of x against log y instead. And let's see how this is going to differ from the exponential curve we had before. So here's the data. First of all, we need to plot minus 1 and minus 1.2, which is down here. That's the first point. Next point, and again, and again, and again. So those are the points we should have. Next up, what we need to do is to do a line of best fit and estimate the equation of that straight line. So what I'm going to do here is just get this ready. And so we need to find two nice points. So for me, I'm thinking that this curve, not curve, rather this line, is going to be, just trying to get it accurate-ish first of all. So maybe about there, and let's say, that looks pretty close to almost all points as far as I can see. That goes through all of these very nicely. So now we need to estimate the equation of this straight line. So let's think about this. We need to work out the gradient. So I can pick the gradient here by picking two nice points. Then I can just work out the change in y divided by the change in x between those points. So one point I can see which seems to be fairly easy to read is 3 and 0.8. So I'm going to put this point here. So the change in y, I'm going to start at 3.8. Likewise, change in x, I'm going to start at 3. And another point which I think is fairly easy to read this line of best fit of mine has gone through -1, -1.2. So I'm going to pick this point down here. So y down here is -1. X down here, sorry, y down here, my mistake, is -1.2. And x down at this point is -1. So gradient is change in y over change in x. So change in y is y1 minus y2. Change in x is x1 minus x2. So as you can see, we're going to get here minus a minus, which gives us a plus. And so this one here, I've just spotted, in fact, what am I playing at? My mistake, everyone. So if you change in y, first of all, this y here is 0.8. Silly me. Sorry, 0.8, not 3.8. I don't know why I thought of 3.8. It's 0.8. Apologies. So yeah, that's correct now. So this top bit here becomes 2. And 3 minus -1 is 4. So the gradient's about 0.5. The y-axis intercept seems to me to be between 0.6 and 0.8, which is therefore minus 0.7. So the y-intercept. In fact, it's not y, is it? It's log y. So log y-intercept is minus 0.7. So therefore the equation of a straight line is log y equals a gradient, which is 0.5, lots of x, plus the constant, so that's y, or variable, equals mx plus c. Here the intercept is negative, so we minus 0.7. So we've plotted the same thing in two different ways. One we've used logs to plot and got a straight line. The other we've just plotted y and x and we've got an exponential curve, which is nothing like what we've got here. This has transformed it into a straight line. So now we need to think about why, when we plot it like this, do we have a straight line, whereas when we've just plotted f of x, we had a curve like what we had before. This is what we need to consider next. So as I was saying, why would the graph of log y and x give us a straight line graph, whereas the graph of x and y gave us an exponential curve? Why this difference? So let's just consider this step by step. And what we need to remember is some things from the other lesson or two, which I'm going to just put in the corner here just as a little reminder to us. So we need to use these laws of logs. Like I mentioned in the other lesson, we can take logs of both sides of an equation in the same way we can perform the same operations to both sides of any equation, log in itself being one such operation. So let's take log of y. So if we do log of y on the left, we need to do log of this on the right. So log of y is the same as log of all of 0.2 multiplied by 3 to the x. So log y is going to equal what? So let's have a look here. We've got a product in these brackets, 0.2 multiplied by 3 to the x. So we can use this multiplication law here. We can split these two products into separate logs. So log of xy is log x plus log y. So in the same way, we can say this is log 0.2 plus log of 3 to the x. Then we can go one step further, looking at the final bit. So I'll just write log 0.2 here. Log 3 to the x, that's a log of an exponential. So look at this power law here, we can use this to help us here. So log x to the power k is k log x. So we can bring this power to the front before the log. So using this idea, we can bring this x to the front before log 3. And now, if you think about it, we're pretty much home and dry. And so if I just rearrange this into a more familiar look and say it's log y x log 3 I'm going to write first, but I'm going to write it log 3 multiplied by x. Whatever log 3 happens to be, it's not a variable, it's a constant. It's not changing, it's no function of x, y or anything. So log 3x plus log 0.2. And again, log of 0.2, whatever that happens to be, is a constant. It's not going to be changing. So now compare this, what we've got here, to the old familiar y equals mx plus c. Y is a variable as log y is a variable. M is a constant, just as log 3 is a constant. Log 0.2 is a constant, just as c is a constant. And you know from now that y equals mx plus c is the very equation of a straight line graph. So here the gradient is log 3, and the y-axis intercept of our graph was log of 0.2. So now we can see why, if we graph log y of log 3x plus log 0.2, we can now see why it gives us a straight line graph. But let's just check in terms of exactly what straight line graph it gives us. From before, when we actually graphed this using a table of values, we got this here for our final straight line. What we got is that log y was 0.5x minus 0.7. So let's just confirm this. So what we're expecting here is that log 3 will be about 0.5, and that log 0.2 should be about minus 0.7, if it does give us the exact straight line graph we're expecting. So let's just check this now. So using the table of values, we got that the gradient was 0.5. So what is log 3? So if we just type log 10 3, we get 0.477. So you can see to one decimal place, that is 0.5. And likewise, if we were to just try now log 0.2, base 10 of course, then log base 10 of 0.2 is minus 0.698, so on and so on. So again, to one decimal place, that is minus 0.7. So now you can see two things, that if we take logs of both sides, we can derive a straight line graph, and as well as that, the gradient and y-axis intercept are exactly the same as what we'd expect from actually graphing it the slow way using a table of values. So let's just put this into action. So generally speaking, if we've got y equals ab to the power x. So again, let's remind ourselves of these log laws. So for any general a and b, take logs of both sides. We get log y equals log of ab to the power x. So log y, we can use the multiplication law, split this product into two separate logs. So we have log a plus log b to the x. Then that final power, we can bring the power to the front, which gives us x log b. And then writing it in the more familiar way, log y equals log b of x plus log a. We can now, in the same way, compare this to the old familiar y equals mx plus c. So it's going to look like a straight line graph, which I'm going to draw in blue, like we've done this writing in blue. So, zoom, there we go, that'll do. So, comparing the y's to log y, x, big X to little x. So the gradient, m, must be log b, and the y-axis intercept, c, must be log a. So we can add this into our graph here. So that's going to be log a. And the gradient is just going to be change in y over change in x. So we just take any 2 points, say here and here. So we can call this here we can work this out and do the gradient of this. So this here is going to be change in x, because our variable is x. Here the variable's log y, so we could plot log y. This will be the change in log y. So the gradient is going to be log b. So the change in log y divided by the change in x, that will tell us what log b is. So that's worth adding down here. So log b is a change in log y over the change in x. So just change in x. Another function type which we can use logs to help us get a easier to understand model is a type y equals a multiplied by x to the power n. This one, again, we can model as a straight line graph by using logs. So as I did before, I'm going to use the 3 laws of logs from a previous lesson to help us to derive a linear relationship for this. So here are the laws now. So again, we're going to start by taking logs of both sides of this equation. So first of all, if we take log y, that will give us log of ax to the n. Now a multiplied by x to the n is in itself a product. It's a product of a and x to the n. So we can use this multiplication law to separate this out into 2 separate logs. So then we can say that log y is going to be log of a plus the log of x to the power n. Now we can use the power law, this one here, to change log x to the n to n log x. And now we're pretty much home and dry. So now I'm just going to rearrange this into a slightly more familiar look. And so here, I'm going to put n first, then log x. I'm going to put log a at the end. So because x and y are variables, it stands to reason that log y and log x are themselves going to be variables, whereas n is a constant, that's not going to change, and log a, whatever that might be, is also a constant. That's not going to change, it doesn't vary. A is fixed, so log a is fixed. So now we can compare this to big Y equals m big X plus c. So you can see again, now case 2, if we take logs, it's now going to have the same general characteristic of a straight line graph, whereas now big Y is like log y. The variable x now takes the form log x. And so instead of plotting y and x, if we were to plot log y and log x, that will give us a straight line equation of the same type as the normal y equals mx plus c. So our variables now are log y, going vertically, and log x, going horizontally. So the gradient of any straight line graph, you know from GCSE, is m, the coefficient of the big X. So it stands to reason here, if we were to do a straight line graph, the gradient will be the power of this function. So again, I'm just going to do the straight line graph so we can sketch in what we know. Okay, so if we were to graph the gradient, that would tell us what n is. So how would we find the gradient of a straight line graph? Well, that's the same as ever, really. So if I just take 2 points on the curve, then the gradient will be the change in the vertical variable, which is normally y, but in this case it's log y. So that's going to be the change in log y. And this step here is a change in log x. And so if we calculated the gradient, which is change in log y over change in log x, that's going to tell us what n is. So that's just worth putting inside a bubble and remembering. So that's m, but of course, what is c? That's the other component to a straight line graph, the intercept. So here, our log y intercept, c, is going to be log a. So if we were to plot a straight line graph, we could look at the intercept. That tells us what log a is. From that, we can then work out what a itself is. And if we plot the straight line graph of this after manipulating it using logs, the gradient would tell us what n is, the power of x. And so those are the two cases which we're now going to apply with a couple of worked examples. So here we go. So worked example 1. We've got a biologist working for US Fish and Wildlife Service, recorded the population of reindeer between 1944 and 1963 on St. Matthews Island in the Bering Sea, off Alaska. I say he was working on this. I should probably say he worked on this. If he was working on that time, good chances are he's dead. So the data are shown in the table below. So first we need to complete this table of values. Sorry for that rather dark joke, that's a bit mean of me. Anyway, so now we just need to take log p of these values here to complete the table. So this is going to be a fairly straightforward thing to do. So next we just take log of 62. Again, because it doesn't say what a base it is, we can assume it's the common log, log base 10. So log base 10 of 62, that gives us 1.7923, etc. So this has been given to 2 decimal places here, so I'm going to give this one here of mine to 2 decimal places too. So that's 1.79. The next one, 271, so if I take log base 10 of 271, that gives me 2.43. The next one, if I take log base 10 of 1350, that gives us 3.13. Next one, log of this number here, log of 3687. That gives me 3.57 to 2 decimal places. And finally, the last one, log of 5890. That gives us 3.77. So, as you can see here, the population clearly isn't linear. It's just exploding massively as the time increases in years, whereas log p seems to be going up in much more even steps. So this stands to reason, like I said before, if we take an exponential function and take logs of it, we can manipulate it into a easier to understand straight line graph. So that's part A. Part B. We need to plot a scatter graph of log p, which we just did the values for, on the graph paper provided on your handout. So here's the graph paper we've got. So I'm just going to whiz through plotting these because plotting a graph isn't too hard. So the first point, 0, 1.46, we add this in. And the next one, 4, 1.79, 8, 2.43, 13, 3.13, 16, 3.57, and 19, 3.77. So that's the points plotted. Part C, it now asks us to draw a line of best fit on the scatter graph. So what you will know how to do in future is to calculate the equation of a straight line graph exactly. But for now, we're going to do this by eye, just sort of by feel. Okay, so what I'm going to do here is just get mine and think about where we could fit it through these points. So I'm going to take something like this. So is that perfect? Is that exactly the same as yours? Probably not, but it's close enough to most of the points. That will do. And so that's a line of best fit. You do yours yourself. If you disagree with me slightly, feel free to do yours in a slightly different way with a slightly different gradient. That's absolutely fine, as long as you're not completely miles off. Part D. What we need to do next is, using this scatter graph, to deduce the gradient and log p-intercept of the line of best fit, and from that work out the equation of the function. So what we need to do here is to just remind ourselves of what we had. So let's have a look at this and think about it. So thinking about it, doesn't really matter if we go for the log p-intercept or the gradient first, but what I'm going to do, I'm just going to do the log p-intercept. So we can see here, on mine at least, yours might be slightly different, and that's fine, as I've said. My log p-intercept, looking at mine, seems to be about 1.4. And now I can work out the gradient too of mine by working out the change in y over the change in x between two different points on this curve. Well, not curve, straight line really. So, what 2 points am I going to pick? To be honest, it doesn't particularly matter, as long as they're 2 points which are easy enough to read and will give me a easy to interpret value. So pick 2 points which are far enough apart so that they're not on top of each other. So the bigger the distance, the better. So I'm going to pick this point here at the end. So that's at 20 and 4. I'm going to pick the intercept itself down here. And so now if I just graph these points, calculate the distance between, so change in x, and of course the change in y, we can then calculate the gradient. So at the top here, log p is 4. I'm being a bit rough and ready by saying change in y over change in x. In fact, it should be change in log p over change in t. So what I'll do, in fact, I may as well change this now just to be consistent and a bit more accurate in terms of what I'm meaning. So it's actually the change in log p over the change in t. Should be accurate, really. So here, log p is 4. Down here, it's 1.4. The change in t has gone from being 20 here to 0 over there. So 20 minus 0. Now we can calculate this using a calculator. So 4 minus 1.4, 20 minus 0. I've got the gradient is 0.13. So now we can say what the line of best fit is. So the line of best fit is going to be log p for y, if you like, gradient multiplied by x, so the gradient is 0.13. Our x is actually t, plus or minus the intercept, so plus 1.4. Next, we need to use what we've got for part D to help us with part E. So part E, we are told now that the actual population, they believe it to be modelled using this formula here, where A and B are constants to be found. So using the line of best fit from before, which I've just put on here again, we need to work out what A and B are now to two significant figures. So if I just remind us what we got for part D, we can now use these values here to work out what we should be getting for A and B. So again, just going back to what I said about case 1 and case 2 when we changed to modelling exponentially. So if I were to just take this P here and the A, B, T and take logs of both sides, we get log P equals log of A, B, T. That can now be partitioned into two separate logs. So we'd have log A and the log of B to the T. And then that itself can be written as T multiplied by log b. So we have log a plus t log b. So now we can compare coefficients. And so what we can see here is that whatever we're multiplying the t by, which in our equation worked out as 0.13, that must be the same as log b. And likewise, the constant at the end, the log p intercept, 1.4, must be the same as log a. So now we can use our knowledge of logs and exponentials to work these out. So, first of all, I can say that log b must equal 0.13. I'm now going to remind myself of a common example of logs which will help to just trigger my memory. So, for example, the log base 10 of 1,000 is the power of 10. I need to raise 10 to get 1,000. So log of 1,000 is 3. So how does the base 10 and the 3 relate to 1,000? Well, 1,000 here is 10 cubed. And so in the same way here, b must be 10 to the power 0.13. So b is 10 to the power of 0.13. And bear in mind we're given this to 2 sig figs. So let's work this out on the class whiz. So 10 to the power 0.13 gives us, to 2 sig figs, 1.3. And likewise, we can work out log a as well. So we're told that log a is 1.4. So in exactly the same way, we can work this out. So a must be 10 to the power 1.4, which we can again use the class whiz to work out. So just toggle back, type in 1.4, 10 to the power 1.4, and we get to 2 sig figs, 25. So in other words, this equation here, not that the question asks that, but just piecing it together because we can now, p as an approximation for the population is 25 multiplied by b, which is 1.3, to the power of how many years after 1944 we're at. Up to a certain point, of course, it can't be modelled like this forever. We couldn't have trillions upon trillions of reindeer, so the model is only valid between certain parameters. Anyway, let's have a look at a second example now. So in this example, we're comparing the brain sizes to 25 different species of mammals with the mass of that mammal itself. But rather than doing it as a linear graph, we've taken a logarithmic graph to make it fit a linear pattern. So it says here, this is really important as well, so don't just dive in trying to work out the intercept and calculating the gradient manually. It does say that for this line of best fit, which is dotted here, that it's got a gradient of 0.75 and its intersect is 0 minus 2.1. So for part A, write an equation for the line of best fit. Using the general idea of y equals mx plus c, we can use this information to just give our answer really quickly. So our y, if you like, is actually log y. Our m, the gradient, is 0.75. So y, if you like, as it were, gradient multiplied by the variable. The variable is normally x, but now we're graphing log x, so it's going to be 0.5 log x, plus or minus the intercept. The minus is going to be a minus intercept here because it's minus 2.1. So it's going to be log y equals 0.75 log x minus 2.1. Part B, using what we just got before, we can now use this answer to determine values of a and b to 2 sig figs. So if we just remind ourselves of what we should be getting from this equation, it says here it's modelled as a y equals ax to the b type of relationship. So again, just let's take logs of both sides of this. So we'd have log y equals log of ax to the b. That can now be separated out using the multiplication law of logs. So that's the same as log a plus log of x to the b. Which is the same as log a, and then this here, the b can be brought to the front and multiplied with log x. So we have b log x. And so comparing to what we have up here, we now know that this b, which comes before the log x, must relate directly to the 0.75. So we know straight away what b is. B is 0.75. So let's write this down. And that's nicely to 2 sig figs as it is. So b is 0.75. Now we need to think about what a is, this constant here. So after separating the variables into logs, we can see that log a is just this constant on its own. So the a must be this intercept here. So log a must relate to the minus 2.1. So we can work out a just by using exponentials. So log a must be minus 2.1. So we can work out what log a is now by taking 10 to the power of minus 2.1. So a must be 10 to the power of minus 2.1. So let's use a class whiz for this. It's going to be a small number because it's 10 to a minus. And we get something to the minus 3. So it's going to have 3 noughts before it, and then 7, 9. So it's going to be 0.00, 1, 2, 3 noughts, 7, 9. So next up, part C, and the final part to it, we're going to use this model now to estimate the brain mass of a mammal with a body mass of 40 kilograms. And so now we can fit these two constants to this model. So y equals ax to the b now becomes y equals 0.0079 x to the power 0.75. So we can just substitute in that x, the body mass, is 40. So brain mass, our estimate at least, is going to be 0.0079 multiplied by 40 to the power 0.75. So let's type this in. So 0.0079 multiplied by 40 to the power 0.75. That gives us 0.125. So to two significant figures, because we've given our values of our constants to 2 sig figs, that's 0.13 kilograms, which in grams is about 130 grams. So that's the exercises done. As ever, now over to you to try these. So just bear in mind, if you're thinking, oh, not again, this is the very last exercise on the algebra part of the Year 12 course. So just do questions 5, 6, 7, 8 and 9 on page 331, exercise 14H, and then you can start considering what lies ahead of you for Year 2. So get this done, and then congratulate yourself for getting to the end of the algebra part of the course for Year 12. Again, thanks very much for listening. Do carry on working hard. Stay tuned for more videos, and you'll hear from me again soon. Okay, thanks again.